Problem, we have given a steam condenser and the outer surface of the thin wall steam condenses at atmosphere. Inlet fluid is water. Water is entering at a temperature of 15 and leaving at 65, and mass flow of water is given as 0.05. This problem is of internal flow and the water is flowing through the at inlet temperature equals to 15 degrees Celsius. Outlet temperature is 65 degrees Celsius and the mass flow of water is given as 0.05 kg per. Since mass flow is given, we can find out mass flow equals to rho multiplied by area multiplied by velocity. That is, indirectly we have given the velocity. So this is a forced convection problem. The steam is condenses on the outside at atmospheric conditions, so temperature of steam will be approximately equals to 100 degrees Celsius, that is the wall temperature. We assume in this case that the pressure at the steam is atmospheric. In any other numerical, if you are given the pressure of the steam, then from the steam table you can check out T saturation. Diameter of the tube is 3 mm, that is 0.05. You want to find out the length of the heat exchanger required. Only we are able to calculate HO, so this problem differentiate from heat exchanger and will attempt only by mass flow is given as a product of density multiplied by area multiplied by velocity. Mass flow is m dot pi by 4 into d square. Density is given to us is, so velocity come out to be 0.0255 meter per second. So let's classify the problem as a forced convection flow through a pipe. The wall temperature is maintained constant, so this is a uniform wall temperature. Check the flow with laminar or turbulent. We'll find out Reynolds number given by rho multiplied by V multiplied by C. LC is equal to D by dynamic viscosity. C is diameter equals to 0.05. Let's substitute the value here. Density is 995. Velocity we have just find out is 0.0255. Static length is 0.05. When the dynamic viscosity, so we'll multiply by rho. It's a 995 multiplied by 0.657 because nu is equal to rho multiplied by mu. Even also write this equation as VLC by nu also. If you calculate this number, you will get 9477, less than the critical Reynolds number for internal flow, that is equals to 2300. So the flow is laminar. In laminar case, normally there are two conditions with an uniform wall temperature and uniform heat flux. This time the steam is condensing at a temperature of 100 degrees Celsius, and during condensation the phase change, and during the phase change temperature of the wall is constant. So we have a uniform wall temperature condition. We have the forced convection, internal flow, and then we have laminar flow, and in laminar flow we have confirmed that this one is uniform wall temperature. Check your table from index, see the link here in your book, my data book, it's a page number 214, and we have a Nusselt number is equals to, for uniform wall temperature is 3.66. Nusselt number is given by HLC by K. We have LC equal to 0.05 and K is equals to 0.6180. LC is 0.05. Get the value of H equals to 5.97 watts per meter square Kelvin. So we have a energy balance here that amount of transferred by convection is same as the amount of heat is equals to rate of change of energy. For LMTD we have to calculate theta I, which is equals to T wall temperature minus Ti, that is TW minus Ti. 100 minus 15 degrees Celsius is equals to 85. Similarly, we have theta O, which is the difference of TW minus TO, that is 100 minus 65 is equals to 35 degrees Celsius. LMTD is defined as theta I minus theta O divided by natural log of theta I by theta O. We have 85 minus 35 divided by natural log of 5 divided by 30. So LMTD is 6.35 degrees Celsius. Change in energy is given by is equal to heat transfer by convection, that is energy balance or law of conservation of energy. We have Q equals to m dot multiplied by C multiplied by O minus Ti equal to surface area of the tube multiplied by H multiplied by LMTD. We have mass is equals to 0.05. P is 4178. TO is 65, Ti is 50, surface area is pi dl, diameter is 0.05, don't know the length L, value of H we have just find out is 45.97 and LMTD is 56.35 and find out the length L is 25.67 meters. That completes the solution. In a particular solar collector of a cylindrical type, energy is collected by placing a tube at the focal line of a parabolic collector and passing fluid to the tube. The arrangement results in uniform heat flux of 2000 watts per meter square. You have to find out the length of the tube as the water intake from 20 to 80 degrees Celsius, and you have to find out surface temperature of water. properties are given to you. So let's assume this is a solar flat plate curve. Water is entering at temperature Ti equals to 80 degrees Celsius and leaves at 80 degrees Celsius. We have a uniform heat flux here of 2000 watts per meter square over the entire circumferential area, that is pi dl, that we called as Q a surface area, 2000 watts per meter square. Let the inlet wall temperature is TW1 and at outlet the wall temperature is TW2. In the case of uniform heat flux, temperature along the wall will be go on increasing as we receive the diameter of the wall tube is 60 mm, that is 0.06 meters. We are given a mass flow rate 0.01 kg per second. So this one is a problem of force convection because indirectly mass velocity we can calculate, and is a case of internal flow. To identify flow is laminar or turbulent, and is a uniform heat flux problem that is already mentioned in the numeric. So from m dot we'll first find out velocity and then we'll check for Reynolds number. So rho multiplied by v multiplied by velocity. Rho is not given. So what we do, we'll calculate the product of density multiplied by velocity. Cross section area is pi by 4 multiplied by internal diameter is 0.06 square. So product of rho into v is basically called as mass velocity, and this mass velocity come out to be 3.53. Characteristic length for the pipe same as the diameter is 0.06 meter. We have a Reynolds number is equals to rho multiplied by v multiplied by LC, which is equals to d divided by mu. Let's put up this value. Rho into v we can directly put out as 3.536. Characteristic length is 0.06 and dynamic viscosity is given as 352 into 10 to the power minus 6. We get Reynolds number equals to 602.85 less than 2300, which is the critical Reynolds number for internal flow. So the flow is laminar. Thus our problem is clearly defined. So we have force convection, internal flow and laminar, and the wall condition is from heat flux. You can check this link for the table, and in the table you will find a correlation was given to you for Nusselt number. Nusselt number correlation was nu equals to 4.36, the constant number. Nusselt number is given by HLC by K. So we can calculate H as 4.36, or K is given as 0.67 and LC is 6. Get value of heat transfer coefficient H is 48.68 watt per meter square Kelvin. We are ready with the heat transfer coefficient, so we have a energy balance now. Rate of change of internal energy, and we can calculate the rate of change of energy is m dot into Cp into To minus Ti. We have a mass flow rate equal to 0.01. P is given is joules is 4187 multiplied by TO, which is equals to, so this gives the value of heat transfer rate as 2512 watts. Now we have Q divided by AS is equals to 2000. We know the value of Q. We can substitute for Q is equal to 2512 and we are able to calculate surface area. So we have 2512 divided by 2000. So required surface area come out to be 1.256 meters square, but by definition surface area is perimeter multiplied by length, that equals to pi dl. We have 1.256 equals to pi equal to 0.06 multiplied by L. So we can get required length of the solar collector is 6.66 meters. To find out the heat transfer wall temperature at inlet, we have Q divided by AS equals to H multiplied by the temperature difference at inlet, which is equals to, first of all we'll calculate at outlet, which is equals to TW2 minus TO. We have 2000, that is the total value of Q divided by AS. H we have find out is 48.68. We don't know the wall temperature at outlet, minus TO is 80. Solve this, you will get TW2 is 121.1 degrees Celsius. This value is naturally higher than 80 degrees Celsius. Then only the heat is transferred from high temperature to low temperature. I will do extra calculation here for inlet temperature. So we have Q by AS equals to H. At inlet we have wall temperature is TW1 and the fluid temperature is Ti. So we have same value of Q divided by AS, that is equal to 2000. H value is 48.68. Don't know the value of TW1 and inlet temperature is 20. So this time also we have wall temperature more than the inlet temperature, 61.08 degrees Celsius. So this is how we can calculate the wall temperature inlet and